Okay, we're going to work on our homework problem. This was homework number 5. Seemed to be a lot of problems associated with that, according to the TA. So let's start with this first problem here. So we've got this is out of another textbook, 117. So we've got air over a city. There'd be a box of 100 kilometers on the side and reaches an altitude of 1 kilometer. And we've got a wind speed of 4 meters per second and a reaction rate at 0.2 per hour is emitted to the box at a total rate of 10 kilograms per second. So we've got a lot of information that's provided on here. Find the steady state concentration if the air is assumed to be completely mixed. So the first question is, what type of problem is this? And so we have obviously steady state. And it's first order decay. And why is that first order decay? Because we've been provided this first order decay reaction coefficient. Look at the units associated with that. So the type of problem we've got are 0 is equal to QCN minus QC. So we're looking for this concentration minus VKC. And so steady state, we can simplify this. And so let's just draw our box. It's the first step of what we're trying to do, or the first step for solving these types of problems. And so we've got our box that's here. We've got 100 kilometers, 1 kilometer, 100 kilometers. And we've got clean air that's coming in. We've also got a point source that is coming in at 10 kilograms per second. And and we've got a reaction decay coefficient. This should be actually a KD. It's equal to 0.2 per hour. And we're trying to find the concentration, the steady state concentration leaving here after some infinite amount of time. And so we can go back and look at some of those example problems from our textbook and set this up quite easily. The one thing we do need to know is what the Q is. Most of our flows have been in Q. So as we know from fluid mechanics, Q is equal to velocity times area. And here we got 4 meters per second as our velocity coming in, and our area is 100 by 1 kilometers. I guess we can put squared on there. And so the key here is to make sure that all the units are indeed correct. We've got concentrations that are provided in kilograms per second. We want to find this concentration in units of micrograms per meter cubed of air. And so can plug these values in. We know what this is based upon this relationship and what's given. The concentration of this is actually equal to 0. We don't have anything that's actually coming inside here. And then we've got Q, so we want to solve for this concentration, and it's also in this part of the equation. So we've done some of these before. Should get a concentration as you put in the values at 10.5 micrograms per cubic meters. And so work that problem, make sure you get that performed correctly. The second challenge is the next problem. This is problem what is this? A problem 118. Gets a little more challenging. So we are trying to find the concentration after. Let's go ahead and read the problem statement up here. So the wind speed drops to 1 meter per second. We have less wind coming in, hence less dilution in here. What would be the concentration of pollutants 2 hours later? And we would assume that pollution concentration would increase because we got less clean air that's coming inside of this reactor. And so if we were to plot this, we would have concentration as a function of time. This would be our initial concentration when that wind speed drops from 4 meters per second to, let's say, 1 meter per second, and we would have something that would look like this. And so we're trying to find the concentration at 2 hours at this time. This concentration here might be our concentration, I'll say steady state, or I might actually say concentration or affinity concentration, our steady state concentration at some unknown time. And I suspect 2 hours is not going to be enough to reach that steady state. So if you look at the textbook, this is a problem that is similar to example 4.5 and example 4.4 in the textbook that has looked at the first order, non-steady state first order decay. And so if we write our equations that we have here, well, the first step, let's just draw this as step number 1, is to determine the steady state concentration at some time here, our steady state concentration and affinity. And we can essentially go through the same calculations that we did with the previous problem and find out what that new concentration is. So if you have this set up on MathCAD, this would be a real easy concentration to solve for. And if you go through these calculations, you'll get a steady state concentration that's a bit higher than what we calculated before at 10.5. This would be 15.26 micrograms per meters cubed. And so now the challenge is to find what that concentration would be after 2 hours, once we have this dilution starting to take effect. And so we get, let's just write our typical mass balance concentration that we have. dm dt is equal to q cn minus q, and I'll just draw this as c minus kCV. All right. One new wrinkle with this is this concentrations that we have here is not really the equilibrium concentration, and it's not necessarily our starting concentration at 10.5 micrograms per cubic meter, but it's actually a combination of the two, C minus C. Let's just call that infinity. All right, so C minus C infinity would be what that is C concentration is equal to. And so we can simplify this. So we have V dm dt is equal to, and we can solve for like terms that are on. Let's bring the q v my plus k. I'll call this kd, our decay coefficient. Kd all that times, and so we substitute this C minus C infinity concentrations that we have on here. So this is actually still quite a complicated equation to solve for. And so if we remember back in that example 4.5, there was a substitution that we would do so we can integrate this cleanly. And so let's say that y is equal to c minus c infinity. All right, so we're going to substitute y into this equation right here. And so we know that the dy dt would be equal to change in concentration over change in time. All right, so whatever that concentration is at that particular time. And so we would go through this, and we can continue to, let's say, solve for this. dy dt is equal to negative q v, our volume, plus kd times y. All right, and so we'd integrate this y over y naught dy, get the like terms, move t over to the right side of the equation, kv plus kd. All right, and so we've got this, and we'll also integrate this over from time to 0 dt. And when we solve for this, we would get y is equal to y naught e to the minus kd plus qv times t. All right, so we know one other substitution that we can do on this equation, that at y naught, so the time at y sub 0 is equal to c sub 0 minus c infinity. All right, so that would be our initial concentration that we solve for in that first step of this problem. And so we can substitute for, put this into the equations as well. And so where we have y naught here, and then y, here we have our substitution that we can put in to this part of the equation. So we actually have two substitutions that would go into this. It's a little more complicated than the examples that we've seen in the textbook before. And solve for this, c infinity is equal to c naught minus C infinity e to the minus, C infinity e to the minus kd plus qv times t. All right, and so let's think about what we have already in this, what's been given to us, what's unknown. And so we know what this is, the final concentration at 15 point something C naught. So we know what that initial concentration was, which was what we saw of 10.5. Know what this is, know what that is. So we know all these other variables. This would be 2 hours. So as we solve this, we're going to need to be sure we that we use the correct units and simplify this, and we would solve for our concentration at 2 hours. And so if you solve for this, you should get, I hope, 12.3 micrograms per cubic meter would be that concentration at after 2 hours. So it's eventually going to make its way up to, we're here at 12.3, and eventually it's going to make its way up to 15.3 micrograms per cubic meter. So a little more challenging problem. Got a lot of substitutions that were put into here, but that should not be too challenging for based upon the differential equations in the math classes that we've had here at the School of Mines. So that's it for this review. Thank you.